this is for the AQA spec, looking at black bodies, and I think this is in double science and triple science. But we're looking at point 2, which is for higher 2 only. It's saying a body at constant temperature is absorbing radiation at the same rate as it is emitting radiation. Well, first of all, let's look at the word. Let's highlight a few of these words. So body, absorbing, emitting, rate. Yeah, that's fine. Okay, and we've got, so a body, first of all, a body is just basically any one thing. So it could be a cup of water, it could be a person, could be a rock, could be anything at all, really. So often when they think of generic bodies, they draw spheres or maybe cubes, but it really just means anything at all. So let's imagine we've taken this cube here, and this cube is, when we have it, is absolute zero. So there is no thermal energy in it whatsoever. There's no heat energy in it whatsoever. It's impossible to do this, but let's just imagine. It's annoying that says OK. It's supposed to be saying 0K, as in 0 Kelvin, so absolute zero. Now what I've done is I've taken this cube and I've put it inside a place of, say, 100 Kelvin. Now, 100 Kelvin is actually very, very small, very, very low, I should say, very, very cold. But we won't bother looking at converting into centigrade for now. We'll just say that it's 100 Kelvin. And what we want to know is, well, what's going to happen here? Well, if there's any heat energy around the outside, and there is, because it has a temperature above absolute zero, then that heat energy is going to go into this cube. Okay? So the heat energy, these arrows can represent the direction of the heat transfer, right? Now, if the energy outside was actually 200, then the energy would be going into the cube much faster. So we can represent that with drawing multiple arrows. So more arrows can suggest how quickly the energy is going in. So how much energy is passing into that body per second, let's say, right? So it's how much it's absorbing the radiation. Okay, that body is absorbing this much radiation. Now, if you have it the other way around, let's say we have, so we're going to get rid of some of these arrows, and now we're going to have a body at 200 Kelvin and in 0 Kelvin, a room of 0 Kelvin. Clearly now the energy is going to be going the other way, because we're heating up the room and the energy from the body is leaving the body and going into external environment. It doesn't have to be in a room, of course. It could just be in open space. And so in open space, it's much colder. And so this would be the emitting. So this is, and my arrows, how many arrows I draw is representing how quickly that energy is leaving. And so that would be the rate. So the body is anything. The absorbing means how much is energy going into it, and emitting is energy going out. Rate is how quickly it's doing it. So of course it doesn't need to be 0 and 200. It could just be any two different temperatures. So 100 now it'd be the equivalent of the change. The difference in temperature is 100. So we can remove the arrows. That's how we drew it earlier on when it was 0 and 100. Now it's 100 and 200. So we can represent that as one arrow there. So let's just read this at a moment more carefully. It says, a body at constant temperature is absorbing radiation at the same rate it is emitting radiation. So eventually, if these temperatures end up being the same, let's say they're both 100, well, there's going to be energy. What the mistake that people make at this point is they think it stops emitting radiation and it stops absorbing radiation. That's not true. Energy is moving around from one place to another all the time, and the difference being is it's emitting radiation and it's also absorbing radiation but it's doing it at the same rate. Okay, so the temperature neither goes up or goes down because the amount of energy is staying constant. It doesn't mean that energy is not moving. It just means that it's not increasing a total amount of energy, because whenever it loses some, it also gains about the same amount. That's always going to happen when the temperatures are equal to each other. So that's what it means when it's trying to emphasize that it's absorbing and emitting at the same rate. Okay, so point 3, it's really just an application of point 2. The temperature of the Earth depends on many factors, including the rates of absorption and emission of radiation. So imagine the Earth is this body. Well, if we are able to if it's able to emit more energy more easily, then it's going to be able to cool down. If it's able to absorb more energy more easily, it's going to be able to heat up. So this is linking us slowly to the idea of global warming, which is looked at in other parts of the specification, but it's kind of taught explicitly, this minor little point here, that if we are going to reduce how easily the Earth emits radiation, which for this purposes we can imagine as losing heat, then the Earth is clearly going to heat up. So I'll get a picture to demonstrate that. Right. So obviously the Earth is more complicated because we have an atmosphere. This rock, it's this body I've drawn up here. It's just energy going in, energy going out, and I've sort of kept it simple at that point. With the Earth, we have this atmosphere, and the carbon dioxide and basically all greenhouse gases, by definition, reflect the radiation back again. So when you're trying to get the energy out of the planet, well, I mean, having some greenhouse gases is obviously good. Otherwise, our planet would be way too cold. But if there's too much of it, if there's not the right balance, then it's going to keep reflecting it back into the surface, and so we're not emitting the radiation quickly enough, and so the planet heats up. So that's really what all point 3 really wants you to say at that point. Let's have a look at point 4. So point 4 is pretty much the same as the previous ones. I guess it's more explicitly talking about how to link temperature, relation to temperature to the balance, which is what I said about these are in equilibrium because the amount of temperature increasing. I mean, yeah, it pretty much says it here. So point 4 is nothing extra. Point 5. Okay, so point 5 is this diagram here. Okay, so that's there's quite a lot of repetition in this, I guess, or like they sort of elaborate on it, I suppose. But that's what all those points mean there. What they don't say is what exactly is a black body. I don't really see that anywhere on this specification, and that's a bit of a shame because it's a lot of people get very confused about what exactly is a black body. So that's down here, isn't it? We looked at that before, and we started to delve into what do we mean by the word black, what do we mean by the word white. I should probably colour that in actually white because at the moment it's just a background. There you go. So black just means it absorbs all light, and the white means it reflects all light. But the difference, the thing that people often forget is that black also emits all the light, okay, and all radiation actually, because light is just a form of radiation, and so we could be talking about infrared and so on. Another thing to know about black bodies, which again isn't mentioned in the specification, is this bit here, and this does come up in your exam questions. I mean, it's definitely in the textbook, so I'm surprised I didn't really see it there. Let's just have another look at it more carefully. Information to how radiation affects the temperature of the Earth. No. Temperature of the body. It's this first point here. Okay. The intensity and wavelength distribution of any emission depends on the temperature of the body. So obviously, if something's hotter, it's going to be emitting radiation. I was talking about heat in general there, but now we're talking about radiation here specifically. So, as in other words, electromagnetic radiation. Before GCSE, you thought of there were three types of heat transfer: radiation, conduction, and convection. And when we talked about radiation, we always said infrared radiation. Well, it's not. That's not really the whole picture. So it's quite accurate though. Most things that are a little bit warm will emit infrared radiation. So that's how you can detect them using an infrared camera. But when you get it hot enough, it will actually emit visible light. So if we look closely at this graph here, what it's saying is, so I'm just to make it a little bit bigger. What it's saying is that the tallest one represents the distribution of wavelengths when something is that hot, which is really, 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 really hot. So in other words, the maximum, the sort of most common wavelength is this kind of violet color here, right at the end of the visible spectrum. But clearly, you can see if you just look beyond that, there's still other radiation being emitted. It's just that we can't see it. So this would be ultraviolet. So anything as hot as this will emit ultraviolet radiation as well. It will also emit all the other colors, including red and lots of infrared as well. But the most common one is this ultraviolet. Also notice that every single wavelength it emits more than for any other temperature. The difference is that for when something is, so there's two main observations here. So we could say this is hot. It's a shame I'm writing it in blue, but anyway, that one's hot, this one's cold, and this one's in the middle, right? And if we draw a dotted line to see where the maximum is, the maximum for hotter substances have a lower wavelength or higher frequency for its maximum. So compared to this one and this one. But also for all wavelengths, the hotter ones have a higher amount. And what I mean by that, so it says with relative brightness. In other words, so for any wavelength of light, the hot one produces more of that wavelength. Okay, so if I wanted to see how much of this particular wavelength does each one emit, well, the hottest one emits the most, medium one emits the medium, and the cold emits the least. But also, each one has their specific peak at a lower wavelength. I hope that makes sense. We'll probably look at some exam questions to see if we can apply that. Okay. So, in other words, if we could say, let's imagine that we just had one thing where we want to know how does the brightness. So it's the brightness along the y-axis. How does the brightness compare with the wavelength for any particular for this particular substance? Forget about if it's hot or cold. We'll just say it's quite warm. And what we notice is that it kind of doesn't really produce anything down here, but then it produces a little bit of this wavelength. So I think what I might do is actually make this bit quite a bit bigger. We need a bit more space, really. Okay, so let's draw it a bit more neatly. So let's say we've plotted. We're going to collect some results. So of a particular thing. So this is wavelength of a particular object. So this is going, and then we'll have we'll say brightness there. Don't forget that wavelength we perceive wavelength as color. So our brain sees a different wavelength, and well, our eyes see a different wavelength, and our brain turns the wavelength into a color, and that's why in our brain we see these different colors, but actually they're just they're just wavelengths of light. So we've got this machine, and it's detecting different wavelengths of different, and it wants to know how bright is the light at that wavelength. So it might start off by saying, how bright is the light of about I don't know, wavelength, say 500 nanometers, and it will give us a brightness. I think it's difficult to come up with a number here, so we'll just say relative brightness, a relative brightness of say 0.4, right? So and so that we plot that point, say here. Okay, let's say that's the brightness there, and that's the wavelength there. Then we do the same for 550, for 600, 700, whatever it might be. Loads of different and loads of different brightnesses, and we keep plotting these points, and we notice that it kind of makes this sort of shape. Okay, so it does that. And so we say, okay, that's how much brightness it gives for this wavelength. That's how much brightness it gives for this wavelength. And the wavelength that produces the most brightness would be this one down here. Oops, this one down here. Okay. So, well, how hot was that object? Maybe it was, I don't know, whatever temperature it was. And we repeat the exact same experiment, but this time we do it with a hotter object. The hotter object, we measured all the different brightnesses for the same wavelength, and every single time they were brighter. But on top of that, the peak for that one was shifted. Whoops, that's not right. The peak for that one, still not getting it right. The peak is shifted to the left. So the peak is up here now. So the most popular wavelength for this new object is more for smaller wavelengths. So this is my hot object, and this is my cold object. And my cold object, the most popular wavelength, for the wavelength that was the brightest for that object was about here. Okay, so that's my cold maximum wavelength. And then the wavelength that was the brightest for the hot wavelength was this wavelength. But also for all wavelengths, the hot one produced a brighter light for all of those wavelengths. Okay, so when you draw them, these lines would never intersect one another. So that's what this is showing here. Is that a bit clearer?